Good morning. This is a presentation over paper number 54, a comprehensive exploration of a parallel prefix adder tree space. This presentation will begin by discussing theoretical background. I will then summarize the current state of the art. Next, I will present the novel contributions of this paper and discuss results. And finally, I will open the floor to questions. Addition is one of the most important operations in computing, used everywhere from ALUs and FPUs to machine learning. However, addition is slow due to the need to propagate the carry. By pre-generating the carry vector, the whole operation can be done parallel. While each digit of a carry does depend on previous digits, this relation can be rephrased using prefix summation. Brandt and Kuhn define a prefix sum operator for the generation of a carry vector. A discussion of this operator is included in the appendix and can be visited upon request, but what is important is that the prefix sum operator is associative, allowing for full organization of carry generation into parallel trees. These diagrams show examples of prefix trees. On the left is a fully serial network, while on the right is a parallel network. Note the reduction in logic levels from n to log of n. Also note, however, that this reduction comes at a cost. The structure on the right has increased fanout, as well as increased need for horizontal wire tracks. In fact, these three parameters of logic levels, fanout, and horizontal wire tracks can be used to classify the space of prefix adder trees. Harris's taxonomy notes that Pareto optimal adders obey the following equation, describing a cross-sectional plane in the three-dimensional LFT space. However, Harris's taxonomy has caveats. It refers solely to the maximum value of each parameter, causing issues such as clearly different networks being classified as identical. In general, it is mainly designed to describe pre-existing structures, and it cannot be applied to non-standard architectures. In order to deal with non-standard architectures, a scheme must be devised to both generate and describe them. Fishburne identifies a no-target transform that converts between valid structures. Zimmerman expands on this idea to synthesize flexible networks for custom performance and arrival time constraints. However, their scheme cannot directly affect wire tracks. Furthermore, it contains complex edge case patterns that can only be resolved through helper transforms. This paper suggests a novel approach to the generation and classification of prefix trees through the use of the following transform group. Each of these transforms represents a trade-off between the three parameters of logic levels, fanout, and wire tracks. This leads to a direct trade-off in the power, performance, and area of a network. For example, a reduction in logic levels typically leads to increased performance at the cost of increased area and power consumption. These point-target transforms can be used to navigate the whole space of non-redundant prefix adder trees. Any valid network can be generated by the repeated application, and edge cases are handled naturally without the need for helper transforms. Importantly, as these transforms are both invertible as well as commutative, any sequence of transforms can be reduced to minimal form. Roundabout, unnecessary steps are cancelled out. This allows for any structure to be identified by a unique sequence and a start point, almost like a DNA signature. The most universal start point is the serial structure, as it is trivial to generate for any type of adder. If each network is then named after its unique signature, generating it is as simple as reading its name in order and applying the corresponding transforms. Furthermore, only a single function is needed to navigate the classic named structures. As discussed in the paper, it consists of just two simple nested loops, and its only argument is the desired direction. The table on the slide was generated by traversing 8-bit adder networks one transform at a time and synthesizing their respective HDL on a 90-nanometer tech node under typical conditions. It contains 8 well-known name structures as well as 30 novel networks. These architectures provide a wide range of trade-offs between performance characteristics. For example, the structure with the lowest EDP turns out to be one of the transitional structures. Essential is a characteristic not evident from this table. Intermediary networks can be used to optimize from non-uniform constraints. Regular architectures will underperform if some inputs are scheduled to arrive earlier than others. A transform-based generation philosophy can be used to optimize for such cases. Planned future work on this topic involves the continued development of this open-source adder generation library. One particular goal is the development of an adder synthesis tool that will optimize based on design constraints, while another is the incorporation of further optimizations such as higher radix, sparsity, and the link equation. I will now open the floor to questions.